Hello there, and welcome to Life Beyond Seen, where curiosity takes a slow breath and the natural world unfolds at a pace meant to calm the mind rather than chase it. Tonight, we're drifting into a part of the planet that most of us never truly picture, yet it holds more danger, more mystery, and more chemical trickery than any jungle, desert, or mountain range you could walk across. We're going down into the deep ocean, into a place where sunlight fades into memory. Pressure folds the water into something heavy and endless, and survival depends on strategies so unusual they almost sound invented. And among those strategies, some of the most surprising involve toxins. Hunters that don't rely on teeth or speed or size, but instead on invisible chemistry, on venom, on poisons that work silently in the dark. It's a world that doesn't announce its threats. It lets them drift, pulse, or disguise themselves as something harmless until the moment they're not. Before we begin sinking into that quiet world together, I'd love to know something simple and grounding. Where are you listening from tonight? Are you close to the ocean or somewhere far from it? Are you winding down after a long day or just looking for a little calm before sleep? It's always interesting to think about how we're all coming to this moment from different places, even though we're sharing the same story for a while. And if you happen to find this journey soothing or interesting or just a nice way to let your thoughts settle, I'd be grateful if you gave the video a like or maybe subscribed. It helps this calm corner reach others who might need a slow-paced escape too. Now, I do hope the details of dangerous creatures don't keep you awake, but even if they do, maybe the gentle rhythm of the ocean and the way life has adapted to its silent challenges will make the experience a little easier to drift through. Because even in the deep sea where toxins rule, there's a quietness to how things unfold. No rush, no chaos, just a constant balance between danger and survival that's been going on for millions of years without any need for dramatic music or sudden movements. When people imagine dangerous animals, the mind usually jumps to sharks or giant squid or something with a lot of teeth. But the deep ocean has a different style. Down there, the most lethal threats are often small, slow, or oddly shaped. They don't chase prey. They don't roar or lunge or break the surface. Instead, they wait, or float, or pulse softly. Many of the most toxic hunters in the deep don't look threatening at all. Some glow in gentle colours, some drift like pieces of fabric, some hide in sand, and some barely move, relying on chemical weapons that don't need to be fast because the moment they make contact, the outcome is already decided. It makes you think a little about how environments shape behaviour. On land, danger is easy to recognise. Creatures that want to intimidate often grow large or appear sharp or bright or loud. But in the deep ocean, where light doesn't reach and sounds travel strangely, none of that helps. So evolution chose a different path. Instead of intimidation, it built efficiency. Instead of speed, it built chemistry. Instead of noise, it built silence. And out of that silence came animals that can end a life with a single brush of their tentacles or a tiny jab from a spine. There's something strangely peaceful about the idea, even though it sounds frightening at first. Not because the animals are harmless, the opposite is true, but because everything in the deep follows a calm logic. Nothing wastes energy. Nothing moves unless it has to. In a place with so little light and so few resources, survival is a matter of patience and strategy, not aggression. A jellyfish doesn't swim around looking for trouble. It simply hangs in the water and lets its venom-coated tentacles drift until something touches them. A cone snail, even though it carries one of the most powerful natural toxins on the planet, doesn't roam or chase. It sits in its shell and waits for the right moment. The deep-sea stonefish doesn't attack, it just sits beneath the sand, and if something presses down on it, the venom does the job, and that's part of what makes the deep ocean so interesting. It's not a place full of monsters, it's a place full of adaptations. Every creature is shaped by the same pressures, the same darkness, and the same quiet. The danger is simply part of the toolkit they developed to survive. As we ease into this journey, It's worth remembering that toxicity is just one way life has learned to protect itself or capture food. It doesn't mean these animals are malicious or aggressive. They don't think about harming anything. They don't plan or seek out violence. For them, venom is the equivalent of a tool, the same way claws or camouflage or endurance help other species. And in the deep sea, where every calorie matters, the most reliable tool is often one that works instantly, silently, and without a struggle. Imagine drifting down through the first few layers of the ocean. At the surface, everything feels familiar. Sunlight sparkles, waves roll, fish dart. But as you sink a little deeper, the colours begin to drain away. Reds disappear first, then oranges, then yellows. Eventually everything shifts into shades of blue and grey. The temperature drops, the pressure increases, the sounds become muffled, and the creatures become stranger. Not strange in a frightening way. More like pieces of a puzzle you've never seen before. Long translucent shapes, soft bodies, slow movements, tiny flashes of light as animals communicate through bioluminescence. It's a world where almost nothing behaves the way your instincts expect it to, and somewhere in that fading light, you see the first signs of how the ocean's toxic hunters survive. There's a jellyfish shaped like a drifting bell, but its tentacles extend much farther than your eyes can trace. Each thread coated with stinging cells so small you wouldn't see them even if you held them up close. A fish might brush against them without ever noticing the danger, and within moments its muscles stop responding. Not because the jellyfish chased it, but because the ocean doesn't reward speed the same way land does. Here, contact is the only trigger that matters. As we keep sinking, the light disappears completely. You wouldn't see your hand even if you held it inches from your face. The only brightness now comes from creatures that make their own. Little pulses of blue or green, soft flickers, slow glimmers. Some of that glow is used to communicate, some to distract predators. But for a few animals, light is a hunting tool, a lure, a way of convincing prey to swim close enough that venom can finish the job. In a place with no sunlight at all, even a small flicker of brightness can feel like a beacon. And predators take full advantage of that. But before we get into the details of these chemical hunters, it's worth grounding ourselves again for a moment. Because talking about toxic creatures can sometimes feel intense, even when the tone is gentle. So take a second to notice how you're feeling. Maybe you're sinking deeper into your pillow or adjusting your blanket. Maybe the room around you is quiet, or maybe there's some soft background noise. Just let yourself settle a little. We're heading into fascinating territory, but we're doing it slowly, calmly, one step at a time. Nothing rushed, nothing overwhelming. The deep ocean is one of the least explored places on Earth. Even today, most of its species haven't been studied. Some haven't even been seen alive by scientists. And among the animals we do know about, many of their toxins are still mysterious. We know how they affect cells, but we don't always know how they evolved, why they're so powerful, or what other roles they might play. The ocean often builds toxins not only for hunting, but also for defense, communication, and even competition. One creature's venom might paralyze, but another's might confuse the nervous system, or slow the heartbeat, or block oxygen from reaching tissues. There's no single definition of what makes an animal toxic. The ocean comes up with many variations. What makes this especially interesting is that toxicity in the ocean isn't concentrated in one type of animal. It appears in jellyfish, snails, fish, worms, starfish, and even some plankton. Toxins show up in tiny drifting organisms and in large predators. Some use poison actively. Others keep it inside their skin as a quiet warning. Some deliver it with a sting, others with a bite, and some use no movement at all, relying entirely on contact. So while tonight we're exploring the toxic hunters of the deep, we're stepping into a subject that touches almost every corner of marine life. And as we continue, the story won't be about danger for its own sake. It will be about how these creatures live, survive, and navigate a world that doesn't follow any of the rules you'd expect. The deep ocean is a place of slow strategies and subtle interactions, and the creatures that rule it do so not through intimidation but through efficiency. So as we begin our gradual descent into this world, keep in mind that nothing here wants to harm you. These animals have lived in darkness long before humans existed. Their toxins are not aimed at us. They evolved for very specific roles, and those roles revolve around survival, not aggression. We're simply observers moving through their environment, trying to understand how they manage to thrive in a place that seems almost impossible to inhabit. And with that gentle drift into the darkened layers of the sea, we can ease into the next part of our journey, where the first of these chemical hunters reveal how they turn the quiet stillness of the deep into an advantage rather than an obstacle. Where toxins aren't sudden shocks but steady, reliable tools shaped by millions of years of challenge, and where survival depends on the smallest movements, the faintest lights, and the most precise chemistry the ocean has ever created. The ocean has a way of hiding its most surprising secrets in places where no one is likely to look. When you imagine danger beneath the water, it's easy to picture something fast or loud or large enough to cast a shadow, but the reality is almost the opposite. Many of the most threatening creatures in the sea don't tower or stalk or chase. They drift, they settle, they glow softly or blend in completely. They're part of a kingdom where toxicity isn't a rare trait but a common language, a place where chemistry takes the role of both shield and sword. And if there's anywhere this becomes clear, it's in the deep parts of the ocean where light disappears long before life does. Once you start thinking about the deep sea as a kind of hidden kingdom, the idea becomes easier to follow. Not a kingdom in the usual sense, with boundaries or rulers or landmarks, but a quiet territory shaped by pressure, temperature, and the slow drift of currents. A world where the creatures that survive here all share one thing. They've learned that the surest way to stay alive is to change the rules of engagement. Instead of fighting with muscle, they rely on tiny molecular structures that can paralyze a fish, slow a heartbeat, or interrupt a nerve signal long before the prey realizes anything is wrong. The ocean didn't give them speed or eyesight or strength. It gave them chemistry. As you picture the deep sea, try to imagine what it's like to live in a place without sunlight. Not dim light or cloudy conditions, but actual darkness. The kind where even the brightest flashlight from the surface would dissolve in only a few meters. Down there, the idea of visibility doesn't work the same way. Shapes fade, edges blur. The horizon disappears completely. Every animal is a shadow against more shadow, and the only way to notice anything moving nearby is through small signs. A ripple of pressure, a faint shift in the current, a quick pulse of light that might mean a meal or might mean danger. In that environment, finding food becomes a challenge that demands a precise and efficient method. Something silent. Something that doesn't require a chase. Something that can end the moment of contact before either animal wastes energy. That's where toxins come in. In this underwater kingdom, they're not exotic or unusual. They're routine. A jellyfish doesn't sting out of anger. A fish with venomous spines isn't trying to be aggressive. A snail doesn't fire its harpoon because it enjoys hunting. They're simply using the only strategies that make sense in an environment where every calorie matters, where movement is costly, where mistakes are rarely forgiven, and where slow, steady chemical certainty is often better than anything dramatic. One of the first things you notice when you think about toxic creatures in the deep is how varied they are. Some have bodies as soft as gelatin, floating with barely any structure at all. Others have spines or shells or long curling tentacles. Some rely on venom to capture prey. Others use it to defend themselves from predators that might otherwise swallow them without hesitation. A few have toxins strong enough to kill animals many times their size. Not because they needed that much power, but because evolution doesn't fine-tune toxicity for humans or larger species. It only adjusts it for what the animal typically interacts with. So a toxin meant to stop a small fish might also stop something larger purely by coincidence. The deeper you go, the more you see how the rules shift. In shallow water, plenty of creatures depend on camouflage or speed. But in deeper zones where light is limited or gone entirely, movement slows down. Camouflage changes from bright patterns to transparent bodies or deep blacks, and toxins become more reliable than anything that requires momentum. It's not that the ocean becomes more dangerous the deeper you go. It simply becomes more efficient in how danger is delivered. Imagine a creature drifting in the dark. It might be a jellyfish with long, ribbon-like tentacles, each coated with cells that work like miniature syringes. These cells are triggered not by thought, but by simple mechanical pressure. If something touches them, even lightly, the cell fires instantly, injecting a tiny dose of venom into whatever brushed against it. The creature doesn't have to aim. It doesn't have to move quickly. It just needs to be present in the right place. In the deep ocean, presence is everything. Now picture a fish with spines along its back. These spines aren't used for attacking. They don't extend or retract dramatically. They simply exist, covered with venom that discourages larger predators from biting down. In an environment where every meal counts, anything that makes a predator reconsider becomes valuable. The fish doesn't have to flash warning colours or inflate itself. It only needs to make the risk outweigh the reward. Many deep-sea predators can't afford to be injured, even slightly. A sting that causes pain or swelling might be enough to keep them from hunting effectively. And that's a dangerous position to be in, so the presence of venom becomes a strong deterrent. And then there are the snails. Slow, quiet, and easy to overlook, yet capable of some of the most sophisticated venom delivery systems in the ocean. These creatures don't swim. They don't chase. They wait. And when something edible passes close enough, they fire a tiny harpoon loaded with venom. It's not a burst of speed or a sudden lunge. It's precision. It's patience. It's a strategy built for a world where a missed opportunity might mean waiting days or weeks for another. In this poison-filled kingdom, each creature is shaped by the same forces but responds to them differently. The darkness encourages caution. The cold slows metabolism. The pressure forces efficient design. And across millions of years, all of these factors push life towards solutions that don't rely on physical struggle. Toxins become a universal answer to a universal problem. How do you feed yourself or protect yourself without expending more energy than you have? But it's not just predators that use toxins. Some of the deep sea's most toxic species are small drifting organisms that don't hunt at all. Their toxins evolved for defense, for the simple purpose of discouraging anything from nibbling on them. Tiny plankton can carry chemical compounds that would incapacitate much larger animals. Certain worms release substances into the water when threatened. Even some starfish have skin coated with toxins that make them unappetizing to fish that would otherwise consume them. This might sound like the deep is overflowing with danger, but it's more balanced than it seems. For every toxic creature, there are species that have developed resistance. Fish that can brush against venomous tentacles without reacting. Crabs that can handle toxins in certain snails. Predators that have learned to eat around the dangerous parts of an animal. The Poison Kingdom isn't a one-sided realm ruled only by the hunters. It's a system built on constant adjustment, every species finding a way to survive the creatures around it. One of the most interesting things about this hidden world is that toxicity doesn't always announce itself. On land, many venomous animals warn you with bright colours or patterns. It's a way of saying, "I'm dangerous, please don't touch me." But in the deep sea, colour doesn't matter because there's no sunlight to reveal it. So many toxic creatures appear completely ordinary. Clear-bodied, dark-bodied, unassuming. You could swim right past them and never know they carried enough venom to paralyse another animal in seconds. This lack of visual warning changes the entire dynamic. Animals must rely on instinct, memory, or experience rather than appearance. A predator might learn through trial and error which shapes to avoid. Some species develop extremely sensitive chemical detection, so they can sense toxins in the water before getting too close. Others simply evolve thicker skin or a slower approach that lets them test their surroundings without committing to a bite. There's something almost methodical about it. Nothing feels rushed. Every interaction seems like a negotiation. A slow, cautious dance where each creature tests its boundaries and the consequences of a misstep can be immediate. But again, none of this feels aggressive. In fact, much of the deep sea feels quiet, steady and surprisingly calm. Even the toxic hunters move gently, using the water rather than fighting it. They drift or hover or remain still. Their power isn't in motion, it's in precision. When researchers describe this part of the ocean, they often emphasize how stable it is. Temperatures don't swing wildly, light levels don't change, seasons barely matter. The environment is consistent in a way that few other places on Earth can match. That stability encourages slow evolution and careful adaptations. Toxins become more refined over time. Venom delivery systems become more efficient. Prey responses become more specific. It's a long-term conversation between species, shaped not by chaos but by small adjustments that build up over millions of years. And because so much of the deep is unexplored, we're constantly discovering new examples. Scientists lower cameras or submersibles and capture footage of creatures we've never seen before. Some glow, some swim like ribbons, some stay pressed to the seafloor. And many are equipped with toxins that researchers don't fully understand. Every new discovery adds another layer to this kingdom, reminding us how much life exists beyond our everyday experience. As we move deeper into the story, it becomes clear that this oceanic kingdom isn't ruled by fear or aggression. It's ruled by survival strategies that make sense in a world without light, a world where the simplest actions can mean the difference between life and loss. Toxins fill that role perfectly. They're efficient, they're silent, they don't require strength or speed. They allow even fragile creatures to defend themselves or capture food. And they create a landscape where danger and beauty often coexist in the same delicate shape. What makes this especially fascinating is how these toxins influence the entire ecosystem. A predator might avoid certain areas because a toxic species is common there. A prey animal might migrate based on chemical signals. Entire food webs can shift because one species has particularly effective venom. The deep ocean isn't shaped by large forces alone. It's shaped by countless small decisions made by creatures with delicate bodies and powerful chemistry. As we continue unfolding this world, we'll meet some of these hunters more directly. Not as monsters, but as examples of how life adapts when the environment demands creativity. We'll see how venom works in creatures that float above the seafloor, how poisons shape interactions among drifting animals, and how even the smallest organisms can influence entire regions of the ocean with the right chemical tools. And with that gradual understanding, we can drift further into the next part, where the quiet world of venom becomes even more intricate, showing how creatures that barely move still manage to rule the deep through contact, patience, and chemistry that never needs to raise its voice. There's something quietly unsettling about the idea of a creature that doesn't need to chase, strike, or roar to defend itself or catch a meal. Something that doesn't lunge or snap or even bother to move quickly. Instead, it simply waits for contact. The danger is real, but the delivery is slow, deliberate, and almost passive. In the deep ocean, many of the most effective hunters rely on exactly that method. They kill not through motion but through touch, and often that touch is so gentle that the prey doesn't realize what happened until the process is already well underway. The first thing to understand about these creatures is that their strategies aren't designed for spectacle. They weren't shaped to intimidate anything. They're built for an environment where silence and patience pay off better than speed or direct aggression. When you picture a predator, it's easy to imagine sharp teeth or bursts of movement. But down here, movement is expensive. Attacking takes energy that most animals can't afford to waste, and missing a strike could mean going hungry for days. So evolution selected methods that don't rely on precision timing, just contact, just a brush. A momentary connection between two organisms that ends the interaction before it even fully begins. Take the drifting gelatinous animals that inhabit the midwater zones. Many have tentacles so fine you wouldn't notice them, even if they were close enough to touch your skin. These threads trail behind them in long, almost invisible curtains. They're coated with microscopic capsules, each one capable of piercing through a surface and delivering a dose of venom that acts on the nervous system. There's no noise, no struggle, no dramatic thrashing. Prey animals simply make contact as they swim. The venom acts before the prey realizes anything unusual happened. Muscles stop responding. Movements slow. The animal becomes still, carried gently along by the same currents that brought it into danger. It's easy to underestimate creatures like these because they look delicate. Their bodies are soft. They don't swim forcefully. They don't have sturdy structures, but their strength lies in the chemical tools they carry, not in their physical form. A single tentacle can hold thousands of stinging capsules. Each one works automatically, triggered by simple mechanical contact. No thought required, no aim, just a natural reaction that has been perfected over millions of years. Some of the drifting hunters don't rely on long tentacles at all. Instead, their bodies are lined with structures that release toxins the moment something touches them. The venom spreads quickly, disabling prey with a kind of slow inevitability. It's not dramatic or chaotic, it's controlled, almost like watching a light fade instead of extinguish all at once. In an environment where sudden movements can attract larger predators, a quiet method has obvious advantages. It becomes even more interesting when you consider that many of these venomous creatures move at a pace that barely counts as motion. They rise or fall with changes in buoyancy. They drift sideways with the current. They're carried rather than travelling. This passive approach isn't a sign of weakness. It's a strategy built around conserving energy. Down here, food doesn't appear often. Every calorie matters. A creature that can disable prey without lifting a limb has a clear advantage over one that needs to chase or overpower its meals. But drifting hunters are only one part of this world. On the seafloor and in the darker layers of the mid-water zone, there are animals that use touch-based venom in completely different ways. Picture a fish that appears still, almost like a piece of the landscape. It doesn't swim in large circles or dart around in search of food. It waits, not just for any prey, but for prey that makes contact. Along its body are spines tipped with venom. These spines aren't used to spear prey with force. Instead, the predator holds its position, blending into its surroundings, and relies on curiosity or misjudgment from passing animals. When something brushes against the spines, even slightly, the venom is delivered instantly. The predator doesn't need to chase. It just needs to wait for the right moment when something comes within reach. This style of hunting requires a certain kind of patience that's hard to imagine in human terms. Days might pass with nothing happening. The animal barely moves, conserving every fraction of energy. But it trusts the environment. It trusts that eventually something will wander too close, and when that moment comes, a tiny touch is all that's needed. Some of the most effective slow-motion hunters aren't fish at all, but invertebrates that have turned patience into an art form. You might picture a snail as something harmless, something gentle, something that could only feed on plants or algae. But certain snails living in the deep have evolved a method of capturing prey that seems almost unreal when you first hear about it. They extend a narrow tube and fire a small harpoon-like structure coated with venom. It's not fast in the way a land animal might strike. It's more like a slow extension, a gentle probing movement, followed by a sharp moment of connection. The venom travels through the harpoon into the prey and begins its work. The prey isn't grabbed or pulled, it simply loses the ability to move. Slowly the snail draws it closer. The venom these snails use doesn't cause explosions of movement or dramatic reactions. It works through steady interference with the nervous system. The prey isn't paralyzed instantly. Instead, its muscles begin to fail one by one. Its reactions weaken. Its movements slow, until eventually it can't do anything except allow itself to be consumed. It's easy to think of venom as a violent tool, but in the deep ocean it rarely looks that way. It's more like a quiet switch being flipped. These creatures rely on the consistency of biochemical reactions rather than force. They trust that the venom will do its job without requiring speed or strength, and the prey, caught off guard, rarely has the chance to understand what happened. Another group of animals that depend on touch-based venom are those that build their entire shelter around the idea of surprise. Some hide under sediment, exposing only small sensory structures that help them detect movement nearby. They don't move until the moment of contact. When something brushes the area around them, they react with a controlled release of venom. The venom doesn't need to travel far. It enters the prey directly through contact with specialized structures, and just like that, the encounter ends. It's an approach that minimizes risk. A creature that stays hidden avoids attracting predators. A creature that only uses venom when necessary avoids unnecessary energy expenditure. And a creature that kills by touch rather than by chase avoids all the complications that high-energy hunting usually brings. The variety of venom in these species is almost endless. Some toxins target muscle cells, some affect nerve signals, some disrupt the immune system, some interfere with breathing. Each venom has its own timing, its own pace, its own strategy. Some act within seconds, others take minutes. In the deep ocean, minutes still count as fast. Prey animals don't need to be incapacitated instantly. They just need to be unable to escape before the predator completes the process. And since movement is naturally slower at such depths due to cold temperatures, even gradual venom works efficiently. It's interesting to imagine how a prey animal experiences this world. It swims or drifts through the dark, unable to see far, using chemical cues or pressure changes to detect danger. It might sense a presence nearby but not realize how close it is to something that can kill with a single touch. There isn't always a warning, no bright colours, no sounds, no thrashing movements, just contact, a brief brush, and then a sensation it can't fight against. Many of these venomous creatures aren't physically built to overpower anything. They rely entirely on their chemical tools. If the venom fails, they don't have a backup plan. That's why their toxins are often so strong. Evolution didn't build them for intimidation. It built them for reliability. Their survival depends on that one moment when two bodies meet in the dark. The slowness of these interactions makes the entire ecosystem feel different from the environments we're familiar with on land. On land, danger often comes quickly. A predator leaps, a prey animal flees, there's noise and motion. But in the deep ocean, danger spreads gradually. A brush of tentacle, a graze of spine, a needle from a drifting organism. It's not a sudden explosion. It's a shift from activity to stillness. What makes this especially compelling is that many of these venom-based strategies evolved independently. Jellyfish developed their stinging cells long before fish evolved venomous spines. Snails developed harpoon-like structures that have no relation to the tentacles of drifting predators. Worms developed secretions that work entirely differently. Even some crustaceans developed their own toxins. The ocean didn't settle on one method. It created dozens of versions of the same idea. A method that works in slow motion, a strategy that relies on touch. What all of these creatures share is an understanding of their environment written into their biology. They know without thinking that speed isn't necessary. They know that in darkness, direct confrontation isn't reliable. They know that by making their bodies into tools, they can hunt without moving, defend without fleeing, and survive without wasting energy. If you think about it long enough, the idea becomes less frightening and more impressive. These animals aren't lurking with malicious intent. They're simply using the only method that allows them to exist in a place where the rules are different. They're reminders that life doesn't always evolve toward the dramatic or the obvious. Sometimes it evolves toward the quiet and the efficient. As you picture these creatures drifting, waiting, or hiding, it becomes easier to see how the ocean shapes its inhabitants. The deep sea doesn't reward those who can strike quickly. It rewards those who can endure. And venom delivered through contact is one of the most dependable ways to do that. From here, the journey moves toward animals that add another layer to this slow-motion strategy. Not only do they kill through touch, but they use light, movement and positioning to bring prey right where they want it. Creatures whose soft glows and gentle displays hide the potency beneath the surface. Creatures that blend invisibility with toxicity in ways that seem almost impossible until you see how the ocean encourages such combinations. Light behaves strangely in the deep ocean. At the surface it shimmers endlessly, bending across waves and bouncing between clouds. But once you move downward, it begins to change. It breaks apart, fading colour by colour, until eventually only a dim blue remains. Go deeper still, and even that disappears, swallowed long before you reach the regions where many of the ocean's most fascinating creatures are living their quiet, slow lives. The darkness becomes complete. It seems absolute, as if nothing could exist here without stumbling blindly through a world that doesn't offer any visual information at all. But that isn't how the deep ocean works. Even without sunlight, the water doesn't stay entirely dark. It glimmers in small flashes. It pulses in drifting shapes. It flickers as something invisible moves past. The deep is filled with light, but it isn't the kind created by the sun. It's made by the creatures themselves, produced through chemical reactions that they carry inside their bodies. These soft lights aren't meant to illuminate the landscape. They're signals, traps, disguises, and tools for survival, and in many cases they hide something else as well. Venom that waits quietly behind a glow designed to draw in whatever happens to be watching. Bioluminescence is one of the most effective tools evolution has ever given to deep-sea life. It's simple in concept but powerful in practice. A chemical reaction inside the animal generates light, usually blue or green because those colours travel farthest through seawater. The glow can be steady or intermittent, faint or bright, scattered or directed. Each species controls it in its own way, turning it on and off as needed. That alone is impressive, but what makes it even more striking is how often this glow is paired with toxicity. Not because light and venom are directly connected, but because they complement each other perfectly in an environment where visibility is rare and trust is dangerous. A small glimmer in the dark can mean many things. It might be a signal from a mate, it might be a warning, it might be an animal trying to camouflage itself by matching the faint light filtering down from above, or it might be a lure, a trick, a way of drawing another creature close enough for toxins to take over the interaction. In the deep sea, a glow can be a polite invitation or the last thing a prey animal sees before losing its ability to move. Consider the drifting animals that use light as part of their hunting strategy. They release small pulses that look like tiny drifting sparks. These sparks don't reveal the predator's body. They don't light up the water around them. Instead, they imitate the natural drift of plankton. Curious fish or small invertebrate sees the glow and swims closer, expecting a harmless encounter. It doesn't realise the glow is attached to tentacles that extend beyond the visible area. Tentacles lined with stinging structures ready to deliver venom the moment something touches them. The prey moves toward the light, unaware that the real threat is invisible. That false sense of safety lasts only until contact is made, and by then the venom is already doing its work. Some creatures take the opposite approach. Instead of creating small glimmers that drift, they produce larger areas of steady light along their bodies. These patches of brightness might seem like vulnerabilities, but they're used to control how other animals perceive the predator. A glowing pattern can break up the outline of a drifting body, making it difficult to distinguish where the creature begins and ends. This confusion gives venomous tentacles or spines more time to work. A prey animal might bump into the predator because it misjudged the distance, expecting the glow to mark an edge rather than a decoy. That moment of contact is enough. Other species use bioluminescence to distract predators. If a larger animal approaches with the intention of feeding, the creature can release a cloud of glowing particles into the water. The sudden brightness creates a temporary visual smokescreen, buying precious moments to drift away. And in a few cases, the glowing cloud isn't just a distraction. It can contain chemical irritants or toxins that cause the predator to recoil, giving the smaller creature a better chance to escape. The deep ocean loves to repurpose tools. Light becomes a defensive tactic when needed, and it becomes a delivery system for chemical protection when the situation demands something stronger. What makes these glowing hunters particularly interesting is how gentle their movements are. They rarely act in ways that would startle another creature. A glow might pulse softly, a tentacle might sway, a lure might drift slightly in the current. Nothing about them suggests urgency. They don't behave like animals that need to capture prey with force. Instead, they use calmness itself as a strategy. Calm movements don't send waves of pressure through the water. They don't startle prey into swimming away. They create a sense of stillness that encourages exploration, and every bit of that stillness is carefully shaped by evolution to bring prey within reach of venom that doesn't announce itself until it's too late. It's worth imagining the perspective of the prey animals that encounter these glowing traps. They live in total darkness, navigating mostly by sensing pressure changes or faint chemical trails. When they see a glow, it stands out in a world without contrast. Light becomes a rare event, something worth approaching. The glow might mean food. It might mean potential mates. It might mean something drifting that looks familiar. The prey animal moves toward it not because it is drawn to danger, but because the glow is one of the few pieces of information it has available. In a place without landmarks or sound, any signal becomes important. Some predators have refined the idea even further, creating lures that mimic specific types of glowing prey. A small pulse that resembles bioluminescent shrimp, a flicker that resembles the swimming pattern of a tiny planktonic creature. These signals aren't accidental. Over millions of years, the patterns have been adjusted to match what prey already seek out. The predator doesn't need to think about it. It simply uses the pattern that evolution embedded into its body. And the venom waits behind that performance, ready to end the encounter once the prey comes close enough. There are species that build entire displays from their bioluminescence. Some have rows of glowing spots that turn on in a sequence, creating the illusion of movement where there may not be any. Others produce pulses that travel across their bodies like slow waves. These displays serve multiple purposes. They can confuse predators, attract prey, or allow individuals to signal one another. In a few rare species, the display is timed with the release of toxin-filled structures that drift away from the body. The glowing display draws attention, and the drifting structures deliver chemicals on contact. The predator or prey follows the glow and finds itself touching something harmful, rather than the creature controlling the light. One of the most fascinating examples is found in animals that use downward-facing bioluminescence to camouflage themselves. They generate a soft glow on their underside that mimics the faint light from above, making their silhouettes disappear when viewed from below. This technique, known as counter-illumination, helps them avoid predators. But some species that use this method also carry venomous spines or tissues. The combination creates a powerful strategy. They remain hidden when they want to avoid detection, but if a predator manages to find them anyway, the venom provides a second layer of defense. In the deep ocean, redundancy can mean survival. A few creatures use bioluminescent organs in ways that seem almost deceptive. They produce light inside small structures that resemble baitfish or plankton. These structures hang from the body or extend outward like short appendages. The glowing shapes move independently, shifting slightly with the current. A small fish sees what appears to be prey and moves toward it. But the glowing structure isn't an animal at all. It belongs to something larger, something equipped with venom or fast-acting chemical tools. The approach might look harmless at first. but the predator only needs that one moment when the fish is close enough to touch. It becomes clear after a while that the deep ocean doesn't treat venom and light as separate ideas. It blends them, merging the power of chemical reactions inside the body with the ability to manipulate the visual world outside it. The result is a suite of adaptations that allow slow, delicate creatures to make use of their surroundings in ways that defy expectations. They don't chase. They don't need to. The light brings everything to them. Even organisms that drift aimlessly can benefit from this combination. Some species carry tiny glowing organelles inside their cells. When disturbed, they flash brightly, stunning or distracting animals that might try to feed on them. The flash itself isn't harmful, but in some cases the organism also releases a mild toxin as part of the disturbance response. The glow buys them half a second. The toxin buys them the rest of their escape. Predators higher up the food chain have learned to anticipate these displays as well. They can track the flashes from animals disturbed by small predators and use that pattern to locate potential prey of their own. It becomes a chain reaction of light, movement and chemistry. And everything in that chain is tied to the fundamental idea that the deep sea rewards those who can use limited information to their advantage. There's another layer to this that's easy to overlook. In the deep ocean, many animals rely on vision even if they live in near total darkness. Their eyes are adapted to spot tiny flashes of light, faint patterns, and glimmers far off in the distance. These eyes don't work like ours. They're tuned to detect changes rather than full images. A glow in the dark stands out even if the shapes around it remain hidden, and that sensitivity makes bioluminescent toxins incredibly effective. A predator sees the glow, focuses on it, and moves closer. It trusts the signal, because in a world with so few visual cues, ignoring any signal could mean missing a meal. But as soon as the predator gets close enough to touch the glowing organism, it realizes too late that the light wasn't meant as an invitation. The venom begins its work, slow but certain. The predator tries to move away, but the effects spread before it can. Muscles weaken, signals falter, and the creature that produced the glow remains still, using almost no energy at all. This interaction happens countless times across the ocean. It shapes how animals migrate. It influences when they feed. It determines where they choose to hide. And because bioluminescence also plays a role in communication and reproduction, the system becomes even more complex. Animals must constantly decide whether a light signal is safe to approach or dangerous. Mistakes can be costly. Despite the risks, bioluminescence remains widespread because it provides so much value. Even venomous species rely on it for more than hunting. They use it to find mates in the dark, signaling with specific patterns. They use it to synchronize their movements during migrations. They use it to warn competitors. They use it simply to blend in. The relationship between light and survival runs deep, and adding toxins to the mix only strengthens the strategy. Thinking about all of this raises an interesting point. The deep sea isn't random or chaotic. It's a world built on careful balances. Bioluminescence acts as both a gift and a risk. Venom acts as both a weapon and a defense. Together they create a landscape where creatures that seem delicate are actually well equipped to handle the challenges around them. Their slow movements, faint glows, and quiet methods aren't signs of weakness. They're solutions that make sense in a place where sunlight never returns. From here, the story continues into the lives of animals that use chemistry in yet another way, not just to paralyze or defend, but to manipulate the rules of biology themselves. Creatures that hijack the chemical systems of their prey, overwhelm nerves, block signals, or alter behavior. It's the next step in understanding how the deep sea shapes its hunters, and how these strategies grew from the same slow, patient world we've been exploring one layer at a time. In the deep ocean, every creature is shaped by a reality where efficiency decides who survives long enough to reproduce and who disappears quietly into the dark. Drifting hunters rely on contact. Glowing predators use light to draw prey toward their toxins, but there is an entire category of life that doesn't just use venom to stop muscles or sting tissue. These creatures take things further. They interfere directly with how biology operates, hijacking chemistry itself in ways that are difficult to imagine unless you understand how fragile the body's internal communication networks can be. These hunters don't overpower, they don't crush, they don't tear, they simply rewrite the rules inside whatever touches them. To understand these creatures, it helps to appreciate how dependent every animal is on chemical signals. Even the simplest movements rely on messages travelling between nerves and muscles. A fish swimming through the dark depends on a chain of chemical reactions that tell it which direction to move and how strongly to push. A drifting invertebrate relies on slow patterns of nerve activity to keep itself oriented. Everything alive needs chemistry to do anything at all, and that dependency creates opportunities for predators that can disrupt those internal conversations with precision. Some of the most effective venomous animals in the deep ocean use toxins designed to interfere with the nervous system. These toxins aren't meant to cause pain or create obvious distress. Pain is a signal that warns an organism to avoid something in the future. Many deep-sea predators gain no advantage from warning their prey. They need silence, not learning. So their toxins work in ways that prevent the prey from sending any signals at all. They block the pathways that nerves use to communicate. They interfere with channels that allow ions to move in and out of cells. They interrupt the chemical triggers that allow muscles to contract. All of this happens without any dramatic movement. It begins as soon as the toxin reaches its target. Picture a small fish drifting through the twilight zone of the ocean. It moves with slow, deliberate motion, saving its energy. It senses a tiny flash of light and swims toward it, not realizing that the flash comes from a predator that has spent its entire life perfecting a venom designed to manipulate biology rather than attack it physically. The fish touches a tentacle or a spine or a drifting filament. The toxin enters its system, and almost immediately the internal processes start to change. The fish tries to move its fins, they don't respond. It tries to flick its tail, nothing happens. It senses something is wrong, but the signals from its nerves aren't reaching the muscles that need to act. The predator doesn't rush forward. It doesn't need to. It waits as the toxin continues to interrupt one chemical process after another. The prey becomes still, not because it was overpowered, but because its body no longer receives instructions. Some toxins are even more specialized. They don't block nerves outright. Instead, they cause the nerves to fire constantly, overwhelming the system. Muscles contract uncontrollably. Movements become erratic. The prey wastes valuable energy until exhaustion sets in. A predator watching this doesn't need to participate in the struggle. It simply waits as the prey's biology turns against itself. Once the movements slow, the predator moves in with calm precision. There are venoms that target the respiratory system. They interfere with how cells process oxygen. The prey doesn't suffocate because something blocks its throat or mouth. It suffocates because the cells themselves can't use the oxygen they receive. Even if the prey tries to swim away, its muscles can't produce enough energy. This kind of toxin might sound brutal, but in the deep ocean, it reduces suffering by ending the struggle quickly. The predator avoids a chase. The prey avoids prolonged distress. Everything is efficient. One of the more interesting aspects of these toxins is that many species develop them not to attack others, but to defend themselves. A fish that can't fight physically can still release a toxin that disrupts the chemistry of anything that bites it. A predator grabs the fish and immediately begins to lose control of its muscles. It releases the fish and retreats. The fish drifts away, slow but alive. Over time, predators learn to avoid these species entirely. The presence of the toxin shapes the entire ecosystem, forcing animals to form new habits, avoid certain areas, or choose different hunting methods. Some species take the idea even further. They produce toxins that don't just disable prey but alter behavior. The prey might swim toward the predator rather than away from it. It might stop responding to pressure changes, making it easier to catch. It might lose the ability to distinguish between safe and dangerous areas. These toxins don't remove movement, they manipulate it, and once the prey is close enough, the predator completes the process with minimal effort. A few organisms release toxins directly into the water around them. These aren't meant for targeted attacks. They're used to create protective zones. When a predator swims through the toxic cloud, its reactions slow, its judgment falters, or its sensory systems weaken. It becomes disoriented. It retreats. This strategy allows slow, fragile animals to maintain space in a world where everything is competing for limited resources. The toxins don't need to kill. They only need to interfere just enough to discourage. There are worms, for example, that live inside tubes on the seafloor. They extend their feeding structures into the current to capture small particles drifting down from above. They have no ability to fight or flee, so they release small amounts of chemicals when threatened. These chemicals don't paralyze. They interfere with the predator's ability to coordinate movement. A fish that expected to strike quickly finds itself unable to align its jaws properly. It hesitates. That hesitation gives the worm time to retract into safety. Some star-shaped animals on the deep sea floor carry toxins in their skin. When touched, the chemicals spread across the predator's mouth or face, weakening the ability to grasp or bite. The predator backs away. The star-shaped creature moves only when necessary, but it survives because its toxins make predators think twice. What makes many of these toxins unique is their precision. They aren't blunt instruments. They target specific pathways. They target very particular types of cells. A toxin might block only one type of ion channel, but leave others untouched. It might affect only certain muscles or only specific nerves. These toxins evolve gradually, shaped by countless interactions over vast stretches of time. Predators push prey to become more resistant. Prey push predators to refine their venom. The result is a level of chemical complexity that seems almost intentional, even though it's simply the product of natural selection working patiently across millions of years. Some of the most notorious chemical hijackers in the ocean are snails with delicate shells that hide needle-like structures. They don't swim or chase, they wait. And when the prey touches them or swims too close, they fire a harpoon coated with venom that interferes with the prey's internal chemistry in multiple stages. First, the toxin affects motor control. Then it affects sensory pathways. Finally, it shuts down the systems that allow the prey to maintain balance. The entire interaction takes place quietly. There is no thrashing, no tug of war. Once the venom reaches the right tissues, the prey slowly loses function. Meanwhile, the snail remains still, saving its energy until the process is complete. Scientists studying these toxins often find themselves surprised at how specific they are. A venom might contain dozens or even hundreds of compounds. Some work instantly, others take longer. Some affect only certain parts of the nervous system. Others target muscles directly. Some amplify signals, others suppress them. Each toxin is like a small tool designed for a specific purpose, and together they create a combination that allows the predator to control the prey's biology with incredible accuracy. Even more intriguing are the species that combine biochemical manipulation with environmental strategies. Certain deep-sea animals release toxins only when the water around them reaches a specific temperature or chemical composition. Others produce venom only during certain stages of life. Some creatures use toxins in different ways depending on whether they're defending or hunting. A chemical that causes paralysis in a small fish might have no noticeable effect on a large predator, but a secondary compound might cause irritation or dizziness, encouraging that predator to leave. There are also animals that coat their eggs with toxins. These chemicals don't harm the developing embryos but prevent other creatures from feeding on them. It's a simple technique that requires no movement at all. The eggs are left drifting or attached to surfaces, and the toxins ensure that predators avoid them. This allows species with fragile young to survive in an environment where unprotected eggs would disappear quickly. The more you consider these examples, the clearer it becomes that the deep ocean favours strategies that take advantage of the body's reliance on chemistry. Everything from movement to vision to digestion depends on chemical processes. Interfering with even one of these can be enough to change the outcome of an encounter, and so the deep sea is filled with species that use toxins not as dramatic weapons but as subtle tools. Predators don't need complex behaviours to succeed. They simply rely on the precision that evolution built into their venom. Prey species don't need speed to survive. They rely on chemicals that persuade predators to choose something else. Chemistry becomes a quiet conversation happening beneath every moment of life in the deep. Sometimes the conversation is cooperative. More often it's a negotiation, and often it's a form of control. As we move forward, these chemical hijackers form the bridge to another group of creatures that take a different approach, not relying on deception or subtlety, but on appearances that hide a level of toxicity completely unexpected from something so visually gentle. Animals that look harmless, delicate, even beautiful, yet carry enough toxicity to end a life with a simple interaction. They're reminders that the deep ocean rarely reveals its intentions through appearance alone, and that danger doesn't always look like danger. The deep ocean has a habit of disguising its most dangerous creatures behind shapes and colours that seem completely harmless. Some of the most toxic animals you'll ever encounter look more like drifting ornaments than predators, more like delicate decorations than threats. Their bodies shimmer with soft light or smooth contours. Their movements are unhurried. Nothing about them suggests aggression. They appear gentle, peaceful and unassuming. Yet behind that appearance is a level of danger that can be difficult to reconcile with their outward calmness. This contrast exists because the deep ocean doesn't use beauty and danger the way the surface world does. On land, bright colours often signal that an animal is toxic. Bold stripes, sharp contrasts, warning patterns, they all announce what the animal is capable of. But in the deep sea, colours fade the moment sunlight disappears. Reds vanish first, then oranges, then yellows, and finally greens. There's no reason to advertise toxicity with patterns if no one can see them. So evolution shaped these creatures into forms that simply fit their environment, not into visually alarming shapes. The result is a collection of animals that look serene but carry some of the most potent toxins in the natural world. Imagine drifting through the dark water and seeing a soft, slow pulse of colour ahead. It might look like the glow of a harmless jellyfish or the gentle drift of a comb jelly. These animals can appear almost hypnotic in how they move. Their bodies ripple as if they're gliding through a dream rather than navigating a real environment. But some of them are armed with venom that can incapacitate other creatures at the slightest touch. The beauty you see is simply a byproduct of their anatomy. The danger is hidden in the fine structures they extend outward, structures that look delicate but serve as their primary method of capturing prey. One of the most striking examples is found in animals that release ribbons of light as they move. To a passing fish, these glowing patterns might seem harmless or even inviting. The lights drift and turn, swirling gently like trails of reflection on a calm surface. But the fish doesn't realise that each ribbon of light comes from a creature equipped with toxic cells, designed to interact with the nervous system of anything that makes contact. The predator doesn't need to move quickly. It only needs to float near something curious enough to approach. These glowing hunters rely on their appearance to draw other creatures toward them. Not intentionally in the way a human might use a lure, but naturally through the way their bodies are structured. Their brightness stands out in the dark. Their movements are smooth and predictable. They don't display jagged shapes or sharp motions that might cause alarm. Instead, they project the illusion of safety. That illusion doesn't last long once contact is made. Some of the most dangerously beautiful creatures don't glow at all. They use transparency instead, appearing almost invisible except for the slight distortion they create as water moves around them. Their bodies are clear, smooth, and glass-like. If you were close enough to see them in person, they'd look like drifting pieces of polished crystal. turning gently in the currents. But these transparent animals often possess toxins that work rapidly, eliminating prey before it has a chance to understand what happened. Their bodies hide not just their organs, but their true nature, masking the threat beneath a near-perfect disguise. What makes these transparent predators so effective is their lack of visual presence. A fish sees nothing ahead and continues forward. A small, drifting creature follows the current without realizing it's moving towards something that can end its life within seconds. The predator doesn't reach out or move toward the prey. It simply exists in the right place at the right time, equipped with the tools to take advantage of the moment. Other animals in the deep rely on soft shapes and graceful movements. Their bodies open and close gently, like petals drifting underwater. Their silhouettes are smooth and rounded. There's nothing about them that resembles a predator in the traditional sense. But touch one of their fine structures, and the effect is immediate. The venom acts with calm precision, shutting down the prey's ability to swim or defend itself. The predator doesn't attack in any obvious way. It continues drifting as though nothing has changed. What's surprising is how many of these dangerously beautiful creatures don't eat large prey. Many feed on small plankton or tiny fish. Their toxins didn't evolve to overpower huge animals. They evolved to secure modest meals in an environment where even small bursts of speed cost more energy than they can afford. A toxin that works efficiently is far more reliable than a chase, and a body that looks harmless encourages animals to come close enough for the toxin to do its job. It isn't just drifting creatures that use this approach. Some seafloor animals are just as deceptive. They might resemble ferns, flowers, or delicate fans swaying gently with the current. To an observer, they look more like plants than animals. Their structures rise upward in branching patterns that catch drifting particles. But those same branching structures can be lined with cells capable of delivering venom the moment something brushes against them. Small creatures searching for food might drift too close and never drift away again. These seafloor animals don't chase their prey. They don't reposition themselves with intention. They simply grow in shapes that match the slow flow of water. Their appearance gives no reason for alarm. They exist among rocks, corals, and sediments like harmless features of the landscape, yet they carry toxins strong enough to ensure their survival in a place where they cannot run or hide. One of the most unexpected groups in this category includes fish that appear to be adorned with patterns or delicate fins that feather outward like soft fabric. Their colours might be muted, but their shapes have a gentle elegance to them. Some are nearly motionless, settling on the seafloor with their fins spread like ornamental fans. Others move slowly, giving no sign that they have venom housed in the spines along their back or their sides. A predator might try to swallow one and immediately regret the decision. The venom interferes with muscle control, making the predator loosen its grip. The fish, still moving slowly, drifts away. Even when these animals defend themselves, they rarely move quickly. Their toxins provide enough security that they don't need to flee. They simply trust that the chemicals they carry will discourage whatever threatens them. And most of the time, the strategy works. Predators learn quickly to avoid creatures with certain shapes, certain textures, or certain ways of moving. These visual cues pair with the memory of unpleasant experiences, creating a kind of ecosystem-wide understanding that beauty can hide risk. The deep ocean doesn't reward bright displays or aggressive behaviour. It rewards stillness, subtlety, and efficiency. And many of the toxic creatures we're talking about take advantage of that by adopting forms that wouldn't look dangerous to anything unfamiliar with them. The beauty is a disguise, but not an intentional one. It's simply a result of the environment shaping their bodies to fit the surrounding currents, light levels, and pressures. The toxins came later, or in some cases earlier, and the combination created animals that can seem almost artistic in motion, while carrying enough chemical power to change an entire food chain. Some predators in this category use what are called adhesive structures in combination with venom. Their bodies might produce small filaments or sticky strands that drift gently from their limbs. These strands look like floating threads or thin ribbons. They don't appear threatening, but when another creature touches them, the adhesive keeps it from swimming away, and the venom does the rest. There's no struggle, no chase, no obvious confrontation. The prey becomes still, and the predator slowly consumes it. Other species release small glowing spheres that drift independently of their bodies. The spheres look like harmless particles of light. They pulse softly, floating as if they're not connected to anything at all. A passing fish investigates the spheres, unaware they're attached to a predator by thin, transparent tendrils. The fish moves close enough for the predator's toxins to reach it, and the encounter ends. The glowing spheres continue drifting, ready to deceive the next creature that passes by. Even more subtle are creatures that incorporate toxins into their outer coating. Their skin or outer membranes carry chemicals that activate on contact. To another animal, they feel soft, smooth, or jelly-like. Nothing about that texture signals danger. But the toxin embedded in the surface begins working as soon as the two bodies touch. It's a form of passive defense that works without any movement or deliberate action. The creature continues drifting or resting exactly as it was before. There are also animals that use their beautiful forms to appear harmless to their own prey. Small fish or crustaceans might view them as part of the drifting landscape, something to hide behind or rest near. The smooth shapes provide cover. The gentle glow offers orientation in the dark. But once the prey gets close, the predator's venom takes effect with a kind of calm inevitability. The prey doesn't flee, it doesn't have time. Its body responds sluggishly to the toxin, and the predator waits for the moment when the prey can no longer escape. Scientists still don't fully understand the full range of toxins used by many of these animals. Some species have never been collected alive. Others are so delicate that they fall apart when handled, and many live at depths far beyond regular research equipment. The chemical structures they use are often incredibly complex, with combinations that interact in ways researchers are only beginning to understand. What's clear, however, is that the deep ocean has produced toxins that are not only powerful but specific, efficient, and elegant in their effects. These toxins don't need to create dramatic reactions. They only need to quiet the prey long enough for the predator to feed. Looking at these creatures, it becomes clear that beauty doesn't signal safety in the deep ocean. Soft features, glowing lights, gentle movements. None of these traits guarantee harmlessness. They often indicate the opposite. But because everything moves slowly and without urgency, there's a sense of calm that surrounds even the most toxic creatures. They're not aggressive, they're not violent. They simply exist in forms that allow them to survive, and the toxins they use are part of that existence, no more malicious than the claws of a surface predator or the camouflage of a forest insect. As the story continues, this theme becomes even more pronounced. The next group of creatures doesn't just rely on toxicity and subtle appearances. They combine deception, patience, and the environment itself to create hunting strategies that turn the slow, heavy darkness of the deep into an advantage. Creatures that use stillness, shape, and chemistry to create ambushes perfectly suited to a world without sound or light. In the deep ocean, survival often depends on choosing the right moment rather than the right speed. The water's cold, the pressure is enormous, and energy is something every creature has to guard carefully. There are no lush forests of plants to graze on, or fields where prey gather in predictable numbers. Food arrives unpredictably, drifting through in waves or scattering in thin trails. For many animals, chasing down prey simply isn't realistic. It would be like trying to sprint through heavy fog, unsure of where your target went after the first movement. Instead, life beneath the waves has developed a more patient approach, and nowhere is that clearer than in the animals that have mastered the slow, deliberate art of the ambush. Ambush predators do not chase. They do not dart or lunge unless the moment is exactly right. They wait, sometimes for hours, sometimes for days, and they trust the environment to bring opportunity to them. When they finally act, it's with precision shaped by millions of years of refinement. Many of them carry toxins designed to ensure that a single successful contact is enough. They don't need repeated attempts, because repeated attempts would cost more energy than they can afford to spend. Instead, they use venom as a way to end an encounter the moment it begins. Some of the most effective ambush hunters aren't large or imposing. They blend into their surroundings so well that even if you passed them within arm's reach, you might not notice anything unusual. Their bodies mimic sand, rock, or sediment. Some bury themselves almost completely, leaving only their eyes exposed. Others flatten their bodies to match the surface beneath them. Their stillness becomes part of the environment. To a passing creature, they are indistinguishable from the landscape itself. This approach isn't unique to the deep sea, but the deep makes it especially powerful. Light is scarce, colours disappear, shadows blur together. A predator that hides well in this environment becomes nearly invisible, and many of these hidden predators carry more than camouflage. They carry venom that ensures their strike doesn't have to be fast or forceful. Once the prey makes contact or comes close enough to receive the toxin, the encounter is decided quickly. One of the clearest examples is found in bottom-dwelling fish that spread themselves along the sea floor. They press their bodies into the sediment, blending until only slight outlines remain. Their eyes track movement above them, watching for shadows or pressure changes caused by drifting prey. These fish don't need to swim upward. They don't need to chase. They wait for the prey to come within range, and when it does, a single swift inhalation or subtle upward movement brings the prey close enough to brush against venom-coated structures. The venom doesn't need to act instantly. It only needs to act quickly enough to prevent escape. And in cold water, where movements are already slowed by temperature, quickly enough doesn't require much speed. There are also creatures that use the seafloor itself as part of their trap. They nestle into rock crevices or burrow into silt, leaving a small opening through which to strike. Their bodies contain venom that enhances their chances of success, ensuring that even if the prey begins to retreat, the toxin will affect its movement. The predator can then pull the prey in without expending more energy than necessary. The ambush itself becomes a controlled interaction, where chemistry finishes what the predator began. On rocky ledges and within coral-like formations, small predators perch in places where currents bring drifting animals through natural pathways. They position themselves strategically, using the environment to funnel prey toward them. These predators often carry toxins in their spines or fangs, which allow them to bite or sting quickly before retreating back into hiding. They don't wrestle or grapple. They deliver a brief interaction and then wait for the toxin to immobilize the prey. Once the prey slows or becomes still, the predator emerges again to complete the process. The deep ocean is full of animals that use this strategy. Some are fish, some are crustaceans, some are worms, some are small gelatinous organisms. Their shapes differ, but the concept is the same. Use the environment as part of the approach, minimize energy expenditure, and rely on venom to secure the outcome. What makes this especially effective is the way the deep sea slows the pace of everything. Water moves sluggishly in the deeper layers. Prey animals conserve energy. Even predators that might swim quickly in warmer, shallower waters become more cautious. It's not a place where high-speed pursuits make sense. So ambush predation becomes one of the most stable ways to survive. And when toxins are added to that approach, the result is a method that works consistently, even in an environment that offers no guarantees. Some ambush predators use body shapes that seem almost decorative. Soft fins spread out like leaves. Skin textures mimic sponges or corals. These appearances aren't meant to attract prey, but they help the predator remain unnoticed. A small fish might hide among the fins of a larger predator without realizing the danger. It might use the predator's body as shelter from currents or other threats. The The predator doesn't move until the moment is right. Then, with a small motion, it exposes venom-tipped structures or delivers a bite that contains toxins designed to take hold quickly in the prey's muscles. The prey becomes still, and the predator doesn't have to chase anything. Ambush hunters of the deep also rely on patience in a way that's difficult to relate to as humans. We often think of waiting in terms of minutes or hours, but some of these animals wait for days. They sit in the same position, hardly moving, saving energy. They don't try to improve their position or seek better opportunities. The cost of movement is too high, so they depend on the rhythm of the ocean, the slow movements of currents, the occasional drift of prey, the natural patterns of the deep. And because the deep ocean is stable, without the dramatic changes of temperature or light that happen at the surface, these predators can wait with confidence. Eventually something will come close enough. Certain species take advantage of chemical signals in the water. They release small amounts of substances that are harmless on their own but attract small creatures. These signals mimic the presence of food or the scent of other members of the same species. The prey investigates, following the chemical trail. It approaches the predator, unaware that the trail doesn't lead to anything beneficial. The predator remains still until the prey is in exactly the right place. Then it delivers venom through a bite or touch. The entire sequence relies on the prey following a natural instinct, not realizing it has been guided into an ambush. Even drifting animals can use ambush strategies. They might not sit on the seafloor, but they can position themselves in currents that reliably carry prey in predictable patterns. Their tentacles extend outward, forming a loose net. Nothing about the structure looks threatening. The predator doesn't chase or move toward anything. The current does the work. When a small creature drifts into the tentacles, venom begins to act. The predator doesn't have to tighten the net or reposition itself. Once contact is made, the toxin ensures the prey cannot escape. Some animals create ambush zones around themselves using gently drifting filaments or adhesive structures coated in toxins. These filaments sway in the water like soft threads. They look harmless, almost decorative, but any creature that brushes against them becomes part of the predator's world. It loses mobility, it becomes slower, it drifts less, and eventually it becomes food. The predator doesn't have to move toward the prey because the prey becomes anchored by the filaments themselves. There are species that employ more elaborate methods, forming structures on the seafloor that funnel prey into narrow areas. These structures aren't deliberate constructions in the way a human might build something. They're simply natural extensions of the animal's body or the result of how the animal positions itself, but the effect is the same. The prey enters a narrowing space and reduces its chances of escape. The predator waits at the narrowest point, delivering venom when the prey passes through. The deep sea also contains predators that hide their venom beneath layers of harmless behavior. They might move slowly or seem uninterested in the surrounding world. They allow small creatures to swim near them or even rest on top of them. Nothing about their posture signals aggression. But when the opportunity presents itself, when the prey is positioned exactly right, they move with surprising coordination, delivering venom that ends the encounter before the prey notices what happened. The predator then returns to stillness as if nothing changed. Among the most interesting ambush strategies is the use of false security. A predator might mimic part of the environment so convincingly that prey treat it as a shelter. They hide beneath the predator's fins or rest near its body. The predator benefits from this trust. It doesn't have to hunt. It simply waits for a moment when the prey is within reach. Then it delivers venom and resumes its stillness. The prey's reliance on the stability of the environment becomes the very trait the predator uses against it. This style of predation creates an ecosystem shaped by careful choices. Prey animals must learn to distinguish between safe resting spots and hidden predators. Some become sensitive to certain shapes or textures. Others avoid resting in areas with particular chemical cues. Predators evolve better camouflage in response. They refine their venom to act more quickly. They adjust their body shapes to blend even more effectively. and so the cycle continues. The ambush traditions of the deep ocean are not flashy or loud. They don't involve high-speed pursuits or dramatic battles. They're built on patience, quiet precision, and the ability to let toxins handle the most difficult part of the interaction. These predators aren't trying to dominate their environment. They're cooperating with it. They're responding to its limitations and its rhythms. And through that cooperation, they've created strategies that function reliably, even in a world where unpredictability is the norm. As we continue moving deeper into this journey, the next creatures we meet bring another perspective to the idea of power in the deep ocean. Not all toxic hunters are large or specialized. Some are tiny, nearly invisible to the naked eye, yet carry toxins far more potent than anything their size should logically allow. They shift our understanding of what it means to be powerful in a world defined by darkness, cold, and pressure. And they remind us that size is rarely the defining factor in the deep. Chemistry is. Power in the deep ocean doesn't look the way most people expect. It isn't built from size or speed or physical strength. It doesn't rely on huge jaws or sweeping movements. Instead, some of the most influential forces in the deep belong to creatures so small you could look directly at them and still not realize what they are. These tiny organisms drift through the water, hidden in currents, resting on surfaces, or passing by in faint clouds. They don't advertise themselves. They barely move. Yet many of them carry toxins so potent that their impact reaches far beyond their size. What makes these small creatures so effective is the same thing that shapes all life in the deep ocean. The environment rewards efficiency. To survive here, an animal doesn't need loud behavior or aggressive tactics. It needs precision. It needs chemistry that works immediately and consistently. It needs a method that doesn't depend on speed, because speed is rare in these cold, dense waters, and for many of the smallest organisms, toxins provide that perfect balance. They let them defend themselves, secure food, and influence predators several times their size. Some of the most notorious small creatures in the deep ocean exist as drifting cells rather than animals with defined shapes. These tiny organisms float freely, carried entirely by the motion of the water around them. They don't have fins or tentacles, they don't chase anything. They're simply present everywhere, a constant part of the water's composition, and yet some of them release toxins capable of affecting creatures far larger than themselves. The toxins they create can interfere with muscle control, respiration, or nerve function. A fish swimming through a cloud of these drifting cells may find its movement slowing before it even realizes what it encountered. These toxins serve many roles. Sometimes they prevent other microorganisms from competing for the same resources. Sometimes they stop predators from feeding on them. And sometimes, entirely by coincidence, they affect animals that were never meant to be targets. The toxins weren't designed with large creatures in mind. They simply evolved to give these tiny organisms a better chance of surviving in an environment where even microscopic life is under constant pressure to conserve energy. A chemical defense requires no movement, no action, and no warning. It just exists as part of the organism's structure. Moving up only slightly in size, there are small planktonic animals whose bodies carry pockets of venom. These animals drift in large numbers, forming faint clouds in the water. If a predator attempts to feed on them, it experiences the effects of the toxins almost immediately. The toxins don't need to kill the predator, they only need to make the predator reconsider. A moment of discomfort or confusion is often enough to convince a larger animal to avoid that type of prey in the future. This simple interaction shapes entire feeding patterns across the deep ocean. Predators learn. They move cautiously. They avoid the drifting clouds that look a little too dense or behave in unusual ways. Some of the most impressive small predators carry venom that seems far too potent for their size. These animals hunt tiny prey, mostly other drifting organisms, but their toxins work with remarkable speed. They deliver paralysis or muscle failure so quickly that escape becomes impossible. These interactions happen silently in the water, unnoticed by anything that isn't directly involved. One drifting creature touches another, and the effect begins immediately. There's no struggle, no chase. The venom works with such reliability that the predator doesn't need to adjust its strategy. What becomes striking once you start looking at these small creatures is how often they shape events far larger than themselves. When a cloud of toxic plankton becomes dense enough, larger animals avoid the entire area. When these organisms reproduce rapidly, their chemicals can alter the behaviour not only of predators, but of prey further up the food chain. The toxins travel through the water and through the bodies of animals that feed on affected prey. The influence spreads, reaching far beyond the invisible creatures that produce the toxins in the first place. Many deep-sea animals feed by filtering the water, taking in huge volumes of it each hour. These filter feeders depend on the abundance of microscopic life, but they must also navigate the risk of encountering toxic organisms. Their filtering methods can reduce the threat, but they aren't perfect. Some toxins pass through their systems, affecting them long after the original organism has drifted away. As a result, entire populations of filter-feeding animals may shift their feeding grounds or alter their behaviour based on the presence of tiny toxic species. Then there are the slightly larger but still remarkably small predators that use venom in direct physical contact. Their bodies carry small structures that function like tiny needles or stinging cells. These structures activate when touched, delivering a controlled release of venom. To another small drifting animal, this is more than enough to end the encounter immediately. And because these interactions happen continuously throughout the water column, the entire food web becomes shaped by these tiny exchanges. One type of creature in particular stands out among these small predators. It moves with soft pulses, its body barely more than a thin envelope of tissue enclosing a simple structure. It drifts quietly, relying on the currents, not its own power. Along its body are small cells capable of delivering toxins. These cells fire automatically when touched. They don't require aim or thought. The moment another creature makes contact, even lightly, the venom is released. The prey slows, becomes still, and drifts toward the predator. The predator doesn't pull the prey in. The water itself completes the interaction. The predator consumes its meal without expending almost any energy at all. Some of the smallest toxic animals don't hunt at all. Their venom exists purely for defense. This might seem unnecessary for a creature that moves slowly or remains still, but defense is essential in the deep ocean. Any creature, no matter how small, is potential prey for something else. A tiny animal with no physical defenses would be consumed rapidly, but a tiny animal with chemical defenses can survive long enough to reproduce. It doesn't need to fight back actively. The toxin ensures predators learn quickly or avoid them altogether. These defensive toxins often work in subtle ways. They might cause irritation in the predator's mouth or gills. They might disrupt the predator's coordination for only a few minutes, long enough for the predator to lose interest. They might interfere with taste or chemical detection, teaching the predator to associate that type of prey with an unpleasant experience. Over time, predators develop strong preferences for other prey types. This helps the toxic species maintain stable populations, even though they remain small and mostly passive. Another group of tiny toxic organisms uses adhesive structures in combination with venom. These organisms drift with long, thin filaments trailing behind them. The filaments themselves aren't harmful, but the tips carry small amounts of toxin. When prey touches the sticky filaments, the venom is delivered. The prey becomes immobilized, and the predator simply waits for the drifting currents to bring the prey close enough to consume. The entire process is passive. The predator doesn't move toward the prey is brought to it. Some of the most surprising toxins come from animals that resemble small jelly-like shapes, barely visible without direct illumination. Their bodies are fragile, breaking apart easily when touched. But this fragility doesn't make them vulnerable. It actually enhances their defense. When the body breaks apart, it releases concentrated toxins into the surrounding water. Any predator that attempted to feed on the organism immediately encounters the released chemicals. The predator backs away, learning not to interact with those shapes again. The organism itself might not survive, but its broken structure protects others of its kind by teaching predators to avoid them. Other species protect themselves in a different way. They incorporate toxic chemicals into their reproductive process. Their eggs or larvae contain small amounts of venom that deter predators from feeding on them. The toxins don't harm the developing young. They're enclosed safely within protective structures. But to a predator, the taste or chemical reaction is unpleasant enough to discourage future attempts. This simple defensive method allows tiny species to survive in an environment where every stage of life is threatened. Some small creatures even use toxins to influence the behavior of the organisms around them. They release chemicals that affect how other animals move, feed, or reproduce. These effects might be subtle, but they accumulate over time. If a tiny organism releases a chemical that discourages predators from entering a certain area, that area becomes a safe zone for many other small species as well. The influence of one tiny toxic creature can therefore ripple across the ecosystem, changing the behavior of animals many times its size. It becomes clear, as you consider all these interactions, that small creatures with powerful chemistry hold a level of influence that seems disproportionate. But the deep ocean thrives on such imbalances. A single type of toxin can alter movement patterns across hundreds of meters. A dense bloom of tiny organisms can shift where predators feed. A drifting creature barely larger than a grain of rice can deliver venom potent enough to immobilize prey 10 times its size. Even though these small organisms don't communicate or coordinate, their combined presence shapes the entire deep-sea environment. They create invisible boundaries that other creatures learn to avoid. They form drifting communities that act like living chemical fields. They set the stage for larger predators, influencing where prey gather and where predators hunt. Their toxins might be microscopic, but their influence isn't. What's especially striking is how calm these interactions appear to anyone observing from the outside. There's no thrashing, no visible confrontation, just slow movement, drifting trails, and tiny glimmers of life passing quietly through the water. Yet beneath that stillness is a network of chemical influence that determines who thrives and who doesn't. These small creatures don't appear threatening, but they hold some of the most effective tools in the deep. As we move forward, the story continues into the realm of creatures that don't drift quietly or hide in the sand. Instead, they float freely through the open water, carried by the currents but equipped with toxins that work the moment they make contact. These predators drift through the dark layers like shadows, unseen until the last moment, shaping the movements of everything around them. In the deep ocean, the line between predator and environment becomes thinner than anywhere else on Earth. Many creatures that hunt here don't take on the shapes we usually expect. They don't have jaws that snap or limbs that lunge. They don't stalk like large animals at the surface. Instead, they drift. Their bodies follow the rhythm of the water, rising or falling with changes in buoyancy, sliding through currents that move slowly in long, steady patterns. They look like pieces of the sea itself. Nothing announces their presence. Nothing reveals their intentions. Yet many of these drifting shapes are among the most dangerous predators in the deep, carrying toxins that act the moment another creature touches them. These drifting predators don't rely on speed. They don't need complex maneuvers or sudden bursts of force. Everything about their survival depends on passive contact. As they float, the water brings prey to them. A small fish brushes past a tentacle. A crustacean drifts into a long filament. A tiny organism becomes tangled in a branching structure that looks like floating debris. The predator doesn't react immediately. It doesn't rush to secure the meal. The venom begins working long before any visible movement happens. The prey slows, becomes less coordinated, and eventually stops resisting altogether. The entire interaction can happen without a single noticeable gesture. One of the defining traits of these drifting predators is their ability to blend completely into the water around them. Many are transparent, their bodies nearly invisible except for faint outlines that catch certain angles of light. Others are soft, loose shapes that mimic pieces of jelly-like material in the water. Some appear as long, thin ribbons that stretch across distances far greater than their central body. To an untrained eye, these animals might look like strands of seaweed or drifting cloth, even though true seaweed cannot grow in such deep, dark waters. But down here, any shape that moves without a defined structure becomes part of the backdrop. Predators use this natural camouflage to let prey come to them without hesitation. A drifting predator might appear completely passive, but its body is lined with specialized structures that function flawlessly. Some have long tentacles covered in microscopic stinging cells. Each of these cells is capable of injecting venom without requiring any conscious decision from the predator. The cells fire automatically the moment they make contact with another creature. A fish might swim into one of the tentacles and feel nothing at first, but almost immediately the toxin begins affecting its ability to move. It tries to turn away, but its muscles respond slower than expected. By the time it realizes something is wrong, the predator has already begun closing the distance. Not through active pursuit, but through gentle movements guided by the surrounding current. Other drifting predators rely on body forms that extend much farther than they appear. Their tentacles might stretch tens or even hundreds of times the length of their central body. These tentacles trail behind them in long, barely visible threads. To a passing creature, the central body might look harmless, but the tentacles function as an invisible net. A fish doesn't see the lines ahead of it. It doesn't know it's entering a zone of danger. Once it makes contact, the venom begins working before the predator even senses what happened. The drifting predator doesn't need to change direction. The prey becomes still, and the current moves them closer together. Some of the most impressive drifting predators use structures that branch into multiple strands, each one lined with cells capable of delivering toxins. These branching patterns float outward in irregular shapes, forming a wide radius around the predator. Anything that enters this radius has a chance of touching one of the strands. The predator increases its hunting area without moving more than a few centimeters. It doesn't need to extend force or chase. The environment handles those tasks. The predator simply waits with quiet confidence, relying on its venom to act on anything that happens to come close. What makes these drifting predators effective isn't just their ability to remain unnoticed. It's the combination of transparency, slow motion, and potent toxins. Prey creatures in the deep ocean navigate mostly by sensing pressure changes, chemical cues, and faint traces of movement. They don't rely on sight the way surface animals do. The drifting predator takes advantage of this by presenting nothing that suggests danger. It doesn't create pressure waves. Its movement matches that of the water. Its chemical signature blends into the background. To a passing animal, the drifting predator feels like part of the environment. Because these predators rely so heavily on passive strategies, their bodies are often fragile. Many can be damaged easily. Some break apart with barely any force. This fragility doesn't make them weak, it makes them efficient. Fragility reduces their energy demands, allowing them to survive in areas where food might not be available for long periods. And when predators threaten them, some drifting species use their fragility as part of their defense. If a larger creature attempts to bite them, the fragile body breaks apart, releasing toxins into the water. These toxins cause irritation, confusion, or digestive distress in the predator, teaching it to avoid similar shapes in the future. It's hard to imagine an organism that protects itself by falling apart, but in the deep ocean that strategy works. The drifting pieces release chemicals that repel predators. Meanwhile, the original organism may regenerate or produce offspring before the predator even realizes it made a mistake. Fragility becomes an asset rather than a weakness. Some drifting predators use bioluminescence to enhance their hunting strategy. They create small flashes or pulsing lights that appear at intervals. These lights don't illuminate their bodies. Instead, they appear to float independently, like small glowing particles drifting near the predator. Prey animals may investigate the glow, thinking it might indicate the presence of food. They approach the light, unaware that tentacles or toxin-bearing filaments are floating nearby. The predator doesn't need to lure them actively. The glow does the work. Once the prey touches the hidden structures, the venom begins its quiet, gradual work. Not all drifting predators generate their own light. Some take advantage of naturally occurring bioluminescent organisms that drift through the water. They position themselves in areas where these glowing organisms are common. The light attracts small animals searching for food. As those animals approach the glow, they drift directly into the tentacles or filaments of the predator. The predator benefits without using any extra energy. It simply holds its position and allows the movement of the water to bring prey into contact. There are species that take a more active form of drifting. They adjust their buoyancy to move vertically through the water column. They don't swim in a traditional sense. They control the density of their bodies, rising and falling with the natural flow. This method allows them to encounter different types of prey at different depths. If prey gather in a certain layer, the predator drifts upward or downward to match that location. Its venom handles the rest. Other drifting predators create floating colonies. These colonies are groups of individuals connected by shared structures, forming networks that can extend many meters. The colony moves as a single unit, drifting through the water. Some parts specialize in feeding, others specialize in reproduction, others provide buoyancy. The collective movement extends the reach of the colony's toxins. Prey entering the colony's range encounters multiple forms of danger before realizing anything is wrong. The colony doesn't act aggressively. It simply exists as a floating system that uses chemistry to sustain itself. These colonies might seem complex, but they operate through simple principles. Each member performs its role. The colony drifts. Prey encounters the colony by accident. The toxins act. The colony absorbs the nutrients. There are no leaders or coordinated strategies, just a structure shaped by evolution to maximize efficiency. One of the challenges prey animals face when dealing with drifting predators is the lack of reliable information. In shallow water, movement creates clear signals. Ripples spread outward. Shadows reveal presence. But in the deep ocean, movement is absorbed by the surrounding water. Sound travels farther, but it's harder to interpret subtle details. Light is nearly non-existent. Chemical cues disperse slowly over time. A prey animal might sense something unusual in the water, but it won't know the shape or distance of the threat. It might swim cautiously, but caution alone isn't enough when the predator's structures can extend far beyond what the prey expects. Some prey animals have developed thicker scales or more resistant tissues to protect against toxins. They might survive the initial contact and swim away before the venom fully takes effect. But even these species struggle with drifting predators that possess multiple types of toxins. A predator might combine neurotoxins with chemicals that interfere with the ability to breathe. Others might use toxins that slow muscle function and cloud sensory perception. A single contact is enough to create vulnerability, and the predator doesn't need to follow up. The weakened prey becomes unable to navigate the water effectively, and within minutes, the current carries it into the predator's central body. Even animals larger than the drifting predators are not immune. Juvenile fish, small crustaceans, and even some mid-sized species can be affected by these toxins. They don't need to be captured forcefully. They simply need to brush against a drifting filament. The predator doesn't need to overpower them physically. The toxin handles that task with a level of certainty that physical force could never match in such an environment. It might seem unusual that drifting predators are so successful, given their slow pace and fragile bodies. But the deep ocean is slow in every respect. Movements are gradual, interactions unfold over minutes rather than seconds. Drifting makes sense. It conserves energy. It allows predators to spread their reach widely, and it lets them take advantage of the water's natural movement. Instead of chasing prey, they let prey come to them. Instead of relying on strength, they rely on chemistry. What makes these drifting predators so effective is how seamlessly they fit into the deep ocean. They don't disrupt the environment. They don't create large disturbances. They behave like the water itself, moving with the currents, blending with the background, and letting their toxins handle the rare moments when another creature drifts too close. As we continue through this world, the next part of the story shifts from individual strategies to the larger patterns of survival. The deep ocean is full of competition, and every creature, large or small, drifting or ambush-based, participates in a long, ongoing struggle shaped by chemistry and patience. The next creatures we encounter push this idea further, showing how evolution turns the deep sea into a slow but precise battleground, where every adaptation contributes to an ongoing arms race carried out silently in the dark. In the deep ocean, nothing stays still for long in an evolutionary sense, even though everything moves slowly in the moment. The water feels calm, the creatures drift patiently, and the darkness hides almost every motion. But beneath that quiet exterior, the deep sea is a constant arena of competition. Every creature, whether large or small, predator or prey, drifting or anchored to the sea floor, participates in a long and subtle struggle shaped by chemistry, patience, and time on a scale that makes human history feel like the blink of an eye. It's a place where evolution operates with methodical precision. Each adaptation is tested, refined, replaced, or reinforced through countless interactions that unfold in silence. And over millions of years, this process has created a kind of arms race that never pauses. The term arms race often brings to mind ideas of speed or escalation, but in the deep ocean it looks very different. It unfolds slowly, sometimes over thousands of generations. The weapons involved are not large or intimidating. They're chemical compounds so small you need specialized tools to detect them. They're structural changes that alter how tentacles behave or how cells react to pressure. They're shifts in behavior that happen almost invisibly because the creatures moving through this world don't express emotion or intention. Yet every interaction between predator and prey feeds into this ongoing workshop, shaping what the next generation will inherit. One of the most significant forces in this evolutionary workshop is the presence of toxins. The deep ocean is full of chemical compounds that affect nerves, muscles, respiration, digestion, and sensory perception. Some toxins act quickly, others gradually. Some disrupt a single process, while others target multiple systems at once. For predators, venom provides a reliable way to capture prey without expending much energy. For prey, resisting or avoiding that venom offers a better chance of survival. These competing pressures create a cycle where each side influences the other. Imagine a small drifting predator whose tentacles are lined with stinging cells. For millions of years, those cells have relied on a particular set of toxins to immobilize prey. The prey, exposed to this venom generation after generation, gradually develops resistance. Not absolute immunity, but enough to survive long enough to escape or at least avoid becoming completely incapacitated. The predator begins to lose meals. Creatures that would have been easy targets slip away. Over time, natural selection favours predators whose venom has changed slightly. New combinations of chemical compounds, new structures that bind more effectively to the prey's receptors. The prey, once more, finds itself pressured to adapt, and the cycle continues. This isn't a quick process. It takes countless interactions and vast stretches of time, but the end result is a toxin more refined than what existed before, and prey that's better at recognizing or resisting danger. Each side responds to the other without intent, simply through the slow filtering effect of survival. The deep sea becomes a workshop where molecules are tested, discarded, or perfected with every encounter. Some predators diversify their chemical strategies. They don't rely on a single toxin, but develop cocktails of compounds that act together. One might interfere with nerve signals, another with muscle control, another with oxygen processing. Prey animals that evolve resistance to one compound still fall victim to the others. This multi-layered approach increases the predator's chances of success, and prey must respond with more complex defences in return. Some may alter the chemistry of their skin or change the structure of their cell membranes. Others might alter their behaviour, swimming slightly differently to avoid drifting too close to dangerous tentacles. Evolution doesn't operate with goals. It works through trial and error, guided by the basic principle that traits which help an organism survive get passed on more frequently. In the deep ocean, where encounters between predator and prey happen slowly but regularly, this process plays out across every level of the food chain. Even tiny creatures participate in it. A microscopic organism might develop a toxin that discourages predators from feeding on it. Predators respond by developing resistance or altering their feeding habits. The tiny organism adjusts its chemistry again, and the cycle continues. Sometimes the arms race pushes species into entirely new strategies. A predator whose venom becomes less effective might begin relying more on camouflaged ambush methods. A prey animal whose resistance grows stronger might become bolder in its feeding habits. These small behavioural shifts ripple outward, influencing the animals around them. In the deep ocean, nothing happens in isolation. Every adaptation affects the larger network of interactions. Consider the drifting colonies that use long, stinging tendrils to capture prey. For countless generations, their toxins were a nearly guaranteed method of securing food. But as some prey species developed resistance, the colonies responded with longer tentacles, increasing their chances of making contact. The prey countered by developing better sensory systems, detecting the presence of the tentacles earlier. The colonies adjusted again, producing tentacles that drifted more freely, requiring less pressure to trigger their stinging cells. And so the cycle continued, each change building on the one before it. This slow escalation shapes not only individual species but entire ecosystems. A predator that becomes more effective can decrease the population of certain prey species, creating opportunities for others to thrive. Those new species enter the arms race, developing their own resistance or venom in response to the creatures around them. Over long periods, the balance shifts repeatedly, producing layers of complexity that continue to build as long as the environment remains stable enough for these interactions to play out. Some of the most interesting participants in this evolutionary workshop are animals that develop entirely novel methods of delivering venom. Rather than relying on stinging cells or spines, they might evolve adhesive structures, specialized appendages, or unusual behaviors that improve the effectiveness of their toxins. Once these new methods appear, they become part of the evolutionary arms race, forcing prey species to adapt in new ways. A prey animal may develop thicker tissues around vulnerable areas, or change its swimming patterns. A predator adjusts again. These cycles continue, gradually refining both predator and prey into forms uniquely suited to the deep environment. There are species that use mimicry as part of the arms race. A predator might evolve to resemble a harmless drifting organism, drawing prey closer. Over time, the prey learns to distinguish the predator from the harmless species through subtle differences in shape or movement. The predator responds by altering its appearance further. This iterative process continues until the mimicry becomes nearly perfect or the prey becomes nearly immune to deception. Often, neither side reaches a definitive advantage. They simply improve their strategies in parallel. Another layer of this arms race occurs between venomous species that compete for similar food sources. One predator might develop toxins that act faster than those of a competitor, securing prey before the other can reach it. Another might develop toxins that keep prey alive longer but immobilized, reducing the risk of attracting unwanted attention. These differences influence how the predators use their venom and how they interact with one another. The competition shapes their evolution in subtle but significant ways. Even the smallest organisms contribute to this process. Tiny drifting cells release toxins to discourage predators from feeding on them. The predators adapt. Other microorganisms exploit the predator's weaknesses. These interactions shape the chemical composition of entire regions of water. A dense bloom of toxic organisms can create environmental conditions that affect animals meters away. Predators avoid certain areas. Prey move cautiously. The balance shifts. In time, the toxins themselves evolve as predators develop partial resistance. The deep ocean provides ideal conditions for this slow, steady arms race. Its environment is stable. Temperatures don't swing dramatically. Light levels remain consistent. Currents move predictably. This stability allows evolution to refine traits over long periods without being interrupted by sudden changes. Species can explore adaptive pathways at a pace shaped by chemical interactions rather than by fast-moving predators or rapidly shifting habitats. Everything unfolds gradually, allowing each adaptation to be tested thoroughly through countless generations. The arms race isn't always about conflict. Some species evolve toxins not to attack but to deter competitors. They release chemicals into the water that discourage other creatures from feeding in the same area. Over time, competitors develop tolerance or avoidance behaviours. The first species adjusts its chemical output. These exchanges influence how resources are distributed across the deep sea, guiding movements and feeding strategies in ways that are more cooperative than combative, even if the organisms involved are unaware of their own roles. There are also animals that use toxins to protect their young. These toxins may coat eggs or larvae, making them unappealing or harmful to predators. Predators, in response, develop strategies to identify which eggs are safe to eat. The species producing toxic eggs responds by refining the chemical signature or increasing the potency of the toxins. The predators adjust again. Each generation brings small changes that add up over time, shaping both sides of the interaction. The deeper you go into this world, the more apparent it becomes that the deep ocean is a laboratory for biological innovation. Not because the creatures are more intelligent or aggressive, but because the environment encourages slow, precise experimentation. Toxins diversify, structures change, behaviours adjust. The arms race becomes a continuous feedback loop, with each species nudging the others into new forms of survival. The fascinating part is how quiet the entire process is. There's no noise, no dramatic clashes, no clear moments where one species wins or loses. Instead, everything unfolds through subtle shifts in relationships and biological processes. A toxin becomes slightly stronger. A prey species develops a small resistance. A predator changes its hunting pattern. The modifications accumulate. Over time, they produce animals so well adapted to their specific interactions that they seem designed for one another, even though the process had no direction beyond survival. As we continue, the next part of the story shifts towards something equally important: the misunderstandings and myths humans often carry when they think about toxic marine life. These creatures are not monsters, they're not malicious, they're participants in a slow and intricate system of survival that has shaped life in the deep ocean for longer than our species has existed. And understanding them clearly means letting go of some of the assumptions that have followed these animals for centuries. When people think about toxic creatures in the ocean, they often imagine something aggressive, unpredictable, or intentionally hostile. Stories tend to drift toward exaggeration. A venomous animal becomes a villain. A simple sting becomes an attack. A drifting predator is mistaken for something that hunts with purpose and malice. These ideas don't reflect the real behaviour of deep-sea organisms, but they persist because the deep ocean is a place most people never see for themselves. It's easy to fill that darkness with assumptions, yet the reality is far more subtle. Toxic marine life doesn't follow the dramatic patterns people sometimes imagine. These creatures don't stalk victims or choose violence. They aren't aware of what humans think of them. They survive using the tools evolution gave them, no more and no less. And most of the misunderstandings stem from looking at the deep ocean through a lens shaped by life on land rather than by the rules of the deep itself. One common mistake is believing that venomous animals in the ocean are naturally aggressive. In truth, almost all of them are cautious and slow-moving. They don't waste energy they can't afford to lose. Many of them don't even have the physical ability to move fast enough to attack anything deliberately. Their toxins evolved as passive tools, meant to capture prey or discourage predators, not to instill fear or cause harm without reason. A drifting creature that delivers venom on contact isn't targeting anything. It's simply doing what its cells are programmed to do. Another misconception is that toxicity means an animal is dangerous to everything around it. But toxins evolve with specific targets. A venom that immobilizes a small fish may have almost no effect on a much larger animal, and many toxins don't affect humans at all. The idea that a venomous creature threatens all life equally comes from misunderstanding how specialized these systems are. A toxin might block a certain type of nerve receptor, but only in species that possess it. Another toxin might disrupt ions in muscle cells, but only in organisms with certain cellular structures. The predator and prey drive these interactions together through evolution. Humans are simply outsiders who occasionally encounter these traits by accident. There's also a tendency to assume that toxic marine life is rare or exotic, found only in extreme environments or unusual species, but toxins are actually common across the ocean. They appear in drifting organisms, buried creatures, colony-forming animals, soft-bodied predators, and even seemingly harmless plankton. Venom is not a last resort or a rare adaptation. It's a major part of how life survives in places where physical strength or rapid movement simply aren't options. The real surprise is not how many creatures are toxic, but how many find ways to use chemistry efficiently without drawing attention to themselves. Some misunderstandings come from misinterpreting the appearance of toxic animals. Creatures that look delicate or beautiful are often assumed to be harmless. Transparent shapes, glowing bodies, soft outlines. These traits appear gentle to the human eye, but in the deep ocean they serve completely different purposes. Transparency hides the animal. Soft shapes blend into currents. Gentle glow patterns mimic drifting particles. A human observer sees beauty. A prey animal sees nothing at all until it's too late. And then there are the creatures that look menacing but pose little actual danger. Some deep-sea fish have sharp spines or ridged bodies that appear threatening. But many of those spines contain mild toxins meant only to discourage predators of similar size. They aren't intended for offense. They aren't built to harm larger animals. Their shape gives a misleading impression, simply because humans interpret sharpness as aggression. In the deep sea, those shapes are practical rather than symbolic. A major misunderstanding is assuming that deep sea animals behave like their shallow water counterparts. People sometimes imagine venomous creatures chasing prey the way certain fish in sunlit waters do, or defending themselves with quick bursts of movement. But cold temperatures and immense pressure slow every physical process. Muscles don't respond the way they do near the surface. Reactions take longer. Energy burns quickly. A high-speed predator would exhaust itself immediately at depth. The environment ensures that almost no animal can rely on rapid pursuit or urgent attack. Slow strategies dominate, and venom is one of the few tools that remains effective without movement. Suspicion toward glowing animals is another common theme. Bioluminescence looks unusual to us. Anything that creates its own light seems alien. Many people assume glowing creatures must be especially dangerous or exotic. But light in the deep ocean is not a symbol of threat. It's a tool used for communication, camouflage, mating, feeding, or distraction. Some glowing animals have toxins. Many don't. The glow itself doesn't imply danger any more than the colour of a bird's feathers implies aggression. Humans simply don't experience darkness intense enough to understand why producing light becomes useful. So the assumption lingers that glowing predators must be rare, frightening anomalies. Even the idea that venom must be fast-acting is shaped by human experience with stings from surface-dwelling species. People imagine toxins that cause immediate pain or instant paralysis. But deep-sea toxins often operate at a pace appropriate for cold environments. A toxin might take several minutes to fully affect a prey animal, because nothing in the deep happens quickly. That timeline doesn't make the venom less effective. It simply reflects the rhythm of a world where everything moves more slowly than we're used to perceiving. When humans encounter these toxins in controlled studies or accidental contact, the timing can seem confusing because our expectations come from terrestrial examples. Fear also tends to amplify misunderstandings. Many people assume that if a creature is venomous, it must pose a threat to humans. But most toxic marine animals are incapable of harming us in any meaningful way. They're too small, or their venom is too specialized, or their delivery mechanism requires specific contact that humans are unlikely to experience. Even animals with potent venom rarely pose a risk without direct handling or accidental interaction. Their toxins evolve for purposes that have nothing to do with large mammals in diving suits or submersibles. Another common mistake is believing that deep-sea toxicity is always about predation. In reality, many toxins evolved for defense, competition, or simple deterrence. A drifting organism might release chemical compounds to discourage predators from biting it. A seafloor creature might coat itself in a substance that makes it taste unpleasant. A small colony might generate toxins that keep other colonies at a safe distance. These uses aren't aggressive, they're protective. They allow creatures with fragile bodies to survive in a world where almost everything can become food for something else. Some misunderstandings go even deeper, stemming from the way humans interpret behavior. For example, when a venomous animal spreads its tentacles or expands its shape, people sometimes describe the behavior as threatening or intentional, as if the animal is trying to intimidate something. But these motions usually serve simple physiological functions. The creature might be feeding, it might be adjusting its buoyancy, it might be reacting reflexively to currents. Any venom delivered afterward is not a deliberate act of aggression. It's simply what happens when another creature touches the wrong part of its body. Humans also tend to attribute intelligence or planning to creatures that use complex toxins. The assumption is that if an animal produces a sophisticated venom, it must understand how to use it or intend the effects it causes. But the evolution of venom doesn't require awareness. Chemical structures change gradually over countless generations. Compounds combine and shift. Receptors adapt. None of it involves planning. The animal simply inherits whatever worked best for survival. Its venom is a product of time, not thought. Some myths are rooted in storytelling. Divers, sailors, and explorers throughout history often exaggerated encounters with marine creatures. A sting became an attack. A drifting organism became a monster. The deep ocean, being unknown and inaccessible, made an easy backdrop for these stories. Toxins became symbols of danger rather than tools of survival. These exaggerations stuck, shaping public imagination long before science had a chance to correct them. Even now, dramatic portrayals in media can keep those ideas alive. Another misunderstanding involves the assumption that toxic creatures are fundamentally different or unnatural compared to non-toxic ones. But venom is simply one of many adaptations. It sits alongside camouflage, speed, armor, and sensory specialization. There is nothing inherently strange about it. It's just a form of chemistry. A jellyfish with venom is no more unusual than a fish with sharp teeth. A drifting colony with toxins is no more extraordinary than a crab with claws. The difference lies in how humans perceive chemical interactions versus physical ones. We can see claws, we can hear teeth snap. We can't see toxins working inside cells. This invisibility leads to mystery, and mystery leads to assumptions. Even scientists sometimes underestimate the complexity of these ecosystems. Many toxins remain poorly understood because collecting samples from the deep ocean is difficult. Delicate creatures collapse under pressure changes. Drifting organisms break apart when brought to the surface. Some toxins degrade quickly, making them hard to study. As a result, early research often relied on limited observations, and those observations sometimes led to incomplete conclusions. When knowledge is incomplete, misunderstandings fill the gaps. But despite all the misconceptions, the reality of toxic marine life is far more balanced and predictable than the myths suggest. These creatures do not seek to cause harm. Their toxins are not personal. Their behaviors are not aggressive. They're simply living tools shaped by an environment that rewards stillness, subtlety, and chemical precision. And once these traits are understood within the context of the deep ocean, they stop seeming dangerous in a sensational sense and start becoming fascinating examples of how life adapts to extreme conditions. As we continue this journey, the next part of the story shifts toward the quiet close of this long descent, where the deep ocean's toxic world becomes less about threat and more about understanding, reflection, and the calm rhythm of life that continues regardless of human perceptions. It's a gentle way to ease out of the darkness, not with alarm but with appreciation for everything that has unfolded along the way. The deeper we've travelled into this world, the easier it becomes to understand why the ocean holds such a firm grip on human imagination. Its silence creates space for thoughts that rarely surface in the noise of our everyday lives. Its darkness slows everything down, asking nothing from us except our attention. Even the creatures that fill this place with their drifting movements and quiet strategies for survival encourage a kind of reflection that feels different from anything on land. They aren't dramatic. They don't try to impress. They simply exist in patterns shaped by time far older than anything we know. Reaching the quiet edge of this journey, it becomes clear that the toxic hunters of the deep aren't defined by danger or violence. They're defined by patience, balance, and a kind of stillness that seems almost unfamiliar when compared to life near the surface. We tend to think of survival in terms of force or competition, but down here survival is built on quiet interactions that unfold slowly, often without any visible movement at all. A drifting creature spreads its filaments into the water. A seafloor animal waits under a thin layer of sediment. A tiny organism releases chemicals that influence the behaviour of animals far larger than itself. There's no urgency, no rush, just steady rhythms guided by the cold and the pressure. When you spend long enough observing the deep ocean, even through imagination alone, you begin to feel how different its pace is. Every movement is softened by the density of the water. Every interaction feels suspended in slow motion. It's a place where nothing relies on noise or brightness. Instead, life builds itself around subtle cues, pressure changes, faint chemical trails, the gentle shift of a current. These cues shape not only how creatures hunt or defend themselves, but how they live day to day. They influence everything from where animals drift to how far they travel to how they choose to rest. If anything, the deep sea feels more like a long, continuous exhale than a world driven by constant urgency. And as we step back from the details of venom, chemical interactions, drifting colonies, and ambush predators, what stands out most is how coherent everything is. The deep ocean doesn't feel chaotic. It doesn't feel hostile. It feels consistent. Toxins aren't anomalies. They're part of the same fabric as bioluminescence, camouflage, slow movement, and the recycling of nutrients that drift downward from the surface. Nothing is separate. Every adaptation is connected to the conditions around it. Even the most potent venom or the most delicate hunting structure makes perfect sense when placed in this larger context. It can be comforting in an unexpected way. The deep ocean, despite its darkness, feels stable. It doesn't change quickly. Creatures here adapt to rhythms that repeat generation after generation. The temperature barely shifts. The currents flow in dependable patterns. The silence remains constant. And within that stability, life finds ways to survive using methods that might look unusual at first, but reveal themselves to be logical when viewed from the right angle. A toxin that seems excessive is simply efficient. A predator that appears frightening is simply conserving energy. A drifting colony that stretches for meters is simply taking advantage of the environment's stillness. Thinking about this place creates a kind of calm that's hard to find elsewhere. There are no bright flashes of conflict, no sudden eruptions of speed. Nothing feels rushed. Even the predators, with all their chemical tools, approach their lives with a kind of patient acceptance. They don't fight against the conditions of their world, they adjust to them. They use what the environment offers rather than forcing themselves against it. In many ways, their survival strategies echo something humans often forget, that moving slowly doesn't mean falling behind, it just means conserving energy for the moments that matter. It's almost strange, in a comforting way, to realize that the creatures we label as toxic hunters are among the most peaceful participants in the ocean's ecosystem. Their movements are minimal, their interactions are controlled, their presence is quiet. Everything about them reflects the nature of the deep itself. They aren't threats in the dramatic sense, they're reminders that life adapts elegantly to whatever conditions it's given. As we drift back upward in thought, leaving behind the drifting colonies, the ambush predators, and the tiny organisms that shape entire food webs, it becomes clear how much of the deep ocean's character comes from its restraint. Even its dangers feel measured. Nothing lashes out recklessly. Nothing wastes more energy than necessary. Danger exists, but it's delivered calmly, almost neutrally, through tools that evolved because they fit the environment rather than because they were meant to frighten or overwhelm. That kind of neutrality is rare in the environments we're familiar with. On land, survival often looks frantic. Animals compete over limited resources, defend territory, and respond quickly to threats. The deep ocean is different. It doesn't reward territorial displays or bursts of speed. It rewards precision, consistency, and a willingness to remain still long enough for the environment to bring opportunity. It rewards patience in a way that makes everything feel more deliberate, and if you stay with that feeling for a moment, it starts to shift something internally. The ocean below doesn't ask for action. It doesn't push or pull. It simply exists in a state that encourages reflection rather than reaction. Thinking about these toxic hunters doesn't provoke fear. It brings a kind of steady awareness, a reminder that even in places that seem inhospitable, life shapes itself gently. It doesn't need to be loud to be effective. It doesn't need to be fast to be powerful. This quiet understanding has a way of settling into the mind like slow-moving sediment. It accumulates gradually as the journey unfolds. By the time you reach this point, it's no longer about individual species or specific toxins. It's about the overall impression of a world that operates with a sense of continuity. A world where change is constant but never hurried. A world where survival isn't a battle, but a long conversation between creatures and the environment that shaped them. There's something grounding about that. It's easy to imagine the ocean as a place of storms and waves, but far below all of that noise is an environment where everything moves at its own unforced pace. It makes any rush we feel above the surface seem temporary by comparison. The deep ocean isn't concerned with schedules or deadlines. Its creatures follow rhythms shaped long before humans appeared, and they will continue following them long after we're done imagining their world tonight. As the journey begins to tilt upward in spirit, the darkness doesn't feel empty anymore. It feels familiar. The drifting shapes you've met, whether small organisms releasing quiet clouds of toxins or larger predators waiting under layers of sediment, become part of a larger pattern that makes the deep feel almost like a second world behind the one we know. Not frightening, just steady. A place where stillness has purpose. The more time you spend with these thoughts, the more noticeable the shift becomes between the deep ocean and the space you're in now. The room around you feels brighter. The quiet of your surroundings feels lighter, not heavy. And maybe, without trying, your breathing slows just a little to match the rhythm of the creatures you've been imagining. They don't hurry, they don't tense, they let the environment guide them, and in this moment, that same approach feels natural. As the surface world begins to come back into focus, the deep remains with you in a subtle way. Not as a source of fear, but as a reminder of how calm life can become when everything unnecessary falls away. The ocean doesn't argue with itself. It doesn't rush to fill silence. It uses darkness as part of its structure rather than something to avoid. There's something reassuring in that, something steadying, as if the deep is quietly demonstrating that even the most unfamiliar places have their own kind of order. Sitting here now, picturing the last glimmers of bioluminescence fading into distance, it becomes easy to imagine the ocean closing gently around everything that lives within it, not shutting anything out, just settling back into its natural state, a soft, uninterrupted rhythm that continues regardless of who's watching. A world that carries its own quiet boundaries shaped by chemistry, pressure, and time. And as you let yourself ease out of the drifting currents of this world, the transition feels unforced. The darkness doesn't vanish. It simply becomes background again. The creatures we've met along the way keep drifting, hunting, feeding, and waiting, exactly as they have for generations. Nothing ends just because the journey pauses. The deep continues holding its patient patterns, the toxins continue doing their work, and the ocean continues gently folding night around everything that depends on its calm.